And the first thing that you have to remember is we're talking about a closed system here, which means that nothing can escape. Often when we talk about reactions, we talk about reactions that go to completion, and that means that we've got 100% conversion here. That means that we start off with a maximum number of reactants, or a maximum concentration of reactants, and then as the reaction proceeds, this concentration of reactants falls, but at the same time we're making products. Doing this kind of thing that we had before, where the concentration of the reactants goes to zero, what we have instead is a situation where the concentration of reactants falls, but it doesn't quite go to zero. And the same with the products. We begin to get more products here, higher concentration of products, but we don't go to that maximum, that 100% conversion that we had before. What that doesn't mean is that the reaction is stuck in the middle. What it means is that we have a fast reaction at the start, but as the reaction proceeds, we begin to get some conversion back to the reactants again. So at equilibrium, we end up with concentrations that remain the same. What you have to remember is this is a dynamic process, and what we mean by that is that it's not just stopped there with equal concentrations or with equilibrium concentrations, but things are continually changing forwards and backwards. The other thing that you have to remember is that equilibrium position can actually change. So here we've got an equilibrium, and on our right we have stickle bricks, red and blue stickle bricks that are joined together to make red and blue molecules, and on the left the red and blue bricks are not stuck together. So what we can do is split up one of these red and blue molecules, and we can stick another two together and swap them over. But we've still got basically what we had before. We've still got 6 stuck together bricks on one side and 4 split up bricks on the other. However, we can swap them over again. This time we're getting some different ones, splitting up 2 stickle bricks there, putting them on the other side, and then Tom's taking 2 stickle bricks, sticking them together and putting them on the right hand side. So we've still got the same concentration, we've still got the same number on each side, but it's different ones are changing each time. If I'd just shown you 2 pictures of the equilibrium each time, you wouldn't have known which ones had changed. So here we've changed the position of the equilibrium, and this time we've only got 4 stuck together pairs, and the rest of them are all split up on the left hand side. And again we're swapping over a pair, and again we end up with the same thing at equilibrium. Now we're swapping over 2 completely different pairs. It doesn't matter which ones are swapping over, they're moving all the time, but if you look at the actual equilibrium, it looks the same. Another model of this uses a snowball fight, and you can find the original on this website here. So we've got Alfie and Otis that are having a snowball fight, but at the beginning Alfie's got all the snowballs and he starts chucking them at Otis. And you can see he's chucking 1, 2, 3 snowballs he's chucking at Otis before Otis decides to start chucking them back again. So then Alfie chucks one at Otis and Otis chucks one at Alfie, and then they pick up another one and they keep chucking them at each other. So overall you've always got 7 snowballs on one side once Otis starts chucking them back, and we've still got 3 on the other side once Otis starts chucking them back again. But it stays the same, whichever actual snowballs they're chucking each other doesn't actually matter. We've still got 7 on one side and 3 on the other, whichever actual snowballs they're picking up. It's a dynamic equilibrium. Okay, we've got 3 on one side, as long as they're both chucking at the same rate. We've got 3 on one side and 7 on the other, and so that remains whichever snowballs they're picking up and chucking. So then you will have met the equilibrium constant Kc. Now the equilibrium constant Kc controls the position of the equilibrium between the reactants and the products. It can change, and the position of the equilibrium can change even if Kc stays the same. Kc can change if you change the temperature. Kc is constant at a constant temperature, but Kc can remain the same even if the actual position of the equilibrium changes, and we'll come to that later. You've got to think about the units for this as well. If you have two lots of x divided by an x, then simply be able to cancel out these two x's and know that it would be x. If you'd written it like this, x squared divided by x, again you could cancel that quite easily and come up with x. You can follow the same principle even with more complex units. So here we've got an equation, we've got N2O4 in an equilibrium with NO2. So this gives us a Kc, an equilibrium constant, which is NO2, the concentration of NO2 squared, divided by N2O, the concentration of N2O4. So on the top we've got moles per decimetre cubed, and it's squared, so our units are squared. On the bottom we've got moles per decimetre cubed, but there's only one lot of them. So just like we had here where we cancelled two things that are the same, we're cancelling out two sets of units here. And so overall, our Kc, our equilibrium constant, will have units of moles per decimetre cubed. So even if you have something a bit more complicated like this, here we've got SO2 reacting with oxygen to make SO3. Our equilibrium constant will be this concentration squared. So on the bottom we've got this concentration squared and another concentration here. So in terms of our units, we're going to have moles per decimetre cubed squared on the top and then squared on the bottom here with an extra moles per decimetre cubed there. So overall, again, we're just cancelling out the similar things. We've got this one squared and this one squared. So overall, we're just going to have moles per decimetre cubed on the bottom, 1 over moles per decimetre cubed. So if we want to invert this so that we haven't got 1 over the units anymore, then we just convert this to moles to the -1, decimetre cubed